Let's look at example 5.3.4. When we're talking about expected value, even though it means the exact same thing as the mean, expected value does have another connotation in that what are you expected to win or lose if you're gambling? Or in the terms of life insurance, what would you expect to gain or lose over some period of time given this situation for life insurance and probabilities? So it turns out that you can talk about insurance, life insurance, car insurance, home insurance, anything like that, in terms of probabilities. And that is how the insurance company analyzes things. They analyze a lot of data. They come up with some empirical probabilities for situations. And then they base your premiums, how much you're paying for that insurance, on those probabilities. So they're still trying to make sure that they're earning money as a company, but also that they have enough money to pay in the event that something happens and you need to make a claim. Here's an example where we're gambling a little bit. You're playing a game with a biased coin. You play each game by tossing the coin once. And you know that the probability of heads is 2/3 and the probability of tails is 1/3. If you toss a head, you pay $6. If you toss a tail, you win $10. If you play this game many times, will you come out ahead? This question right here at the end, this is asking about the expected value. Will you come out ahead? That's meaning, are you going to make money off of this game, or are you going to lose money off of this game? Let's see what will happen. First, define a random variable x. Well, let's let x be the amount of money that we win or lose. And I know the book says something like amount of profit. It's the same idea. And then they give us a table, win, lose, x, p of x, stuff. If we win money, that means we tossed a tail when we tossed the coin. And if we lose money, that means we tossed a head. Okay? So in creating our table, though, we need a numerical value for x and then our probability. So I'm going to fill in our probabilities because we know tossing a head is 2/3 and tossing a tail is 1/3. I know that given up here in the table or in the problem. If I toss a head, I pay $6. So that means I'm going to lose $6. Yes? Yes. If I pay $6, I'm losing it. If I toss a tail, I win 10. That means I'm gaining 10. I don't need that plus sign in front of the 10 because I know 10 is positive without the plus. But I do want to point out one thing. With this type of table, when you're talking about gambling or insurance claims or anything doing with losing money and gaining money, x taking on a negative value is acceptable in these situations. The idea of a discrete probability distribution comes from the fact that we have a countable number of values for x. Not necessarily that the x values themselves are whole numbers. They could be cents, in which case we could write them as decimal numbers, for example. But just the fact that x is countable. So, calculating expected value or the mean, we would calculate x times p of x plus x times p of x. We could also make Excel calculate it or Google. So instead of us doing it, let's make Google do it. X p of x, we had win 10 is rolling a tail, and that's 1/3 of the time. Losing 6 is 2/3 of the time. And we can calculate x times p of x just like we did in the last example. Click on x times, click on P of X, grab that handle, drag it down, add them together, and we get our expected value, negative 0.67, if we're rounding to cents. And so we can say here, forgot my negative 0.67 cents. That is our expected value. We are not coming ahead. If we play this game over and over and over again, on average, we're going to lose 67 cents per game. That's what expected value means. On average, what's going to happen? The saying that the house always wins, this is because their expected values are already set up in favor of them, which means they're against you. So if you were to try to calculate your expected value for a game in a casino, your expected value would be negative. That's how they make money.